To be able to calculate the current rating or the ratings for the employed inductor and the ratings, the maximum voltage and RMS current for the employed capacitor, we'll need to find an expression for the current in the RLC circuit, as well as an expression for voltage. So to do that, what we are going to do is we're going to analyze the model of the resonant converters that we discussed. And for an RLC circuit, we know that there are three parameters. We have the resistance R, which we said it's Ri plus R, small. We have the capacitance L, and the inductance L, as well as the capacitance C. Now, these are the three parameters that are sufficient to fully define the RLC circuit. You can also fully define an RLC circuit via another three parameters, which are omega node, Z node, and QL. So what are the values of omega node, Z node, and QL in terms of RL and C? Well, first of all, omega node, we know that there's the radiant center frequency, which is 1 over square root L over C. Z node is essentially the characteristic impedance of the RLC circuit. And what does that mean? Well, it's basically the ratio between the amplitude of the capacitor voltage. So amplitude, I'm gonna represent it as V capital C, which means the voltage for the capacitor. M is essentially mean the peak value. So the amplitude of the sinusoidal voltage across the capacitor divided by the amplitude of the current in the RLC circuit. So we have here voltage across the capacitor. It has an amplitude V capital CM, and then we have a current in the circuit, RLC circuit I, that has a peak value or a maximum value IM. The ratio between the capacitor voltage amplitude and the RLC current amplitude is defined as the characteristic impedance of the RLC circuit. And so we know that if the amplitude of this capacitor voltage is equal to essentially the amplitude of the current in the RLC circuit, this current, and we just multiply it by 1 over omega node C. And so IM cancel IM, and then we have the characteristic impedance as 1 over omega C. Okay. Now, we know that omega node is given by this expression. So we can replace omega node by 1 over square root LC multiplied by C. This will give us essentially, if we do the math, L over C or square root of L over C. And that's basically the characteristic impedance of the RLC circuit. We have what is the loaded quality for the circuit. So we know we defined omega node, we defined Z node. Now what's the QL? L stands for loaded quality, and I'm gonna come back to this in a moment. And we know that for an RLC circuit, its quality is given as can be expressed in terms of the reactance of the inductance, which is omega node, the ratio between omega node L divided by R, where R is essentially R small plus Ri. And that's basically also equal to, if we express it in terms of the capacitor, omega node C R. And if we simplify this expression or replace omega node by 1 over square root LC, So we have 1 over r, then omega node we replace it by 1 over square root LC, and then we have L. So this will give us 1 over r square root L over C. And we know that square root L over C is Z naught. So it's basically Z naught, the ratio between the characteristic impedance and the resistance R. So this is called the loaded quality. So what is the unloaded quality factor? As the name suggests, unloaded means when you remove the load, what will be the quality factor? Well, the inductor of quality is going to be essentially, so the unloaded quality Q node, essentially the quality in terms of the inductor, it will be omega node L divided by R small. And in terms of the capacitor, it will be omega node C R small. And in terms of the characteristic impedance, it will be Z node divided by R small. Now, as I mentioned, just to recap, for a second order RLC circuit, we have 3 parameter RLC, or equivalently, the other 3 parameters that we can represent fully define this RLC circuit with is omega node, Z node, and QL. Now, to find the RMS current rating for the inductor as well as the saturation current as well as the RMS current for the capacitor, what we need is we need to find an expression for the current I in the RLC circuit. And to find an expression for the current I, all we need to do is essentially find the equivalent impedance of the RLC circuit, and then by dividing the voltage or the fundamental component of the voltage by Z, we can find the current, the sinusoidal current in the RLC circuit. We know that this RLC circuit essentially will only allow the fundamental component to flow, so the current is going to be, assuming the quality is higher, the loaded quality is high, larger than 2.5, will be pure sinusoid. So essentially, to find that current, the fundamental, we just need the fundamental component of the voltage divided by Z, and that's how we get I, the function of time. So first, we need to find the impedance Z of this RLC circuit. Well, we know that Z is equal to, all of this is, we call it R, capital. So Z will have 2 components, real component, which is R, plus an imaginary component, which is given by J, times omega L, the reactance of the inductor. And then we have the reactance of the capacitor, minus 1 over omega C. Now we can take R as a common factor, just to put the impedance in a more formal form. If we take R as a common factor, we'll end up with this expression. And then if we take omega node as a common factor from this second term, we'll have R times 1 plus J, and then we have omega node L divided by R. We have omega L divided by omega node L minus 1 over omega node omega LC. Well, and so we can cancel L with L. Omega node over L, that's basically the quality, the loaded quality. And then we have omega over omega node minus LC, we can replace it with omega node squared, right? And then we can cancel this square with this. So we end up with omega node divided by omega. Now, what I'm trying to do is basically, instead of expressing the impedance as a function of R, L, and C, I want to express it as a function of omega node, Z node, as well as the loaded quality QL. Now, let me, we just need, right now we have QL, omega, and omega node. And the only remaining parameter is R, we need to replace that. So we're going to multiply again the R inside. And then let's take Z node as a common factor. So if we take Z node as a common factor, we divide the first term by Z node. G, Q, R divided by Z node. And then we have omega over omega node minus omega node over omega. And so we know that we said the loaded quality QL is equal to what? The ratio between the characteristic impedance of the RLC circuit divided by the resistor R. And so we can replace the first term here, this one, by 1 over QL. So we have Z node 1 over QL plus, in here we have QL as Z node over R, and then we multiply that by R over Z node, so they cancel each other, and we end up with omega over omega node minus omega node over omega. And as you can see, this is the expression for the equivalent impedance of the RLC circuit as a function of Z node, QL, and omega node. And this expression is the equivalent impedance of the RLC circuit as a function of R, L, and C. Now we know that this Z, we can express it in polar form by its magnitude E, J, psi in polar form. And of course, in Cartesian, it has a real part and an imaginary part. So what is the value of Z? Well, the value of Z amplitude is, or magnitude, is essentially going to be Z node square root the x part or the real part square plus the imaginary part square and the value of psi, well, the real part, or sorry, the imaginary part, if we represent it in a triangle, right, we will find it as the imaginary part we have omega over omega naught minus omega naught divided by omega, and of course we multiply by z naught, and the x dimension will be z naught divided by ql. And so the angle psi is given by tan inverse or arctan the y divided by x, and so we have omega divided by omega naught minus omega naught divided by omega, multiplied by Z node, and then divide by the x dimension, so we have Z node divided by QL. Z node will cancel Z node, and we end up that psi is equal to tan inverse QL multiplied by omega over omega node minus omega node divided by omega. Okay. Now, the real part we know to convert from polar to Cartesian will be equal to magnitude of Z cosine psi, and the imaginary part will be the amplitude or magnitude multiplied by sine psi. This expression for the real part, that R is equal to magnitude of Z cosine psi, we'll use a lot to find the current in the RLC circuit. And so essentially we're going to replace the magnitude Z as the ratio between R divided by cosine psi later on. So it will be nice to find the expression for cosine psi. Well, we know this dimension. Let's drop Z because it's common for both. So the x dimension is just 1 over QL, and the y dimension is given by this expression. And so this dimension will be the x dimension square plus the y dimension square. And so cosine psi is given by the x dimension, which is 1 over QL, divided by this dimension, so we have again here omega node over omega. We have here 1 over QL, and then we have here 1 over QL square plus omega node minus omega node over omega square. So cosine psi is given by the x dimension 1 over QL divided by the square root Now we can enter this QL into the square root, so we have 1 over, if we enter it here, QL squared divided by QL squared plus QL squared omega over omega node is minus omega node over omega squared. And so this will cancel that, and we'll find that cosine psi is given by 1 over square root 1 plus QL squared omega over omega node minus omega node over omega squared. Okay. Now, if we look at this impedance expression and try to graph it. So first of all, let's look at the magnitude of Z, the impedance, versus the normalized frequency. So let's put this as F over F naught. So we know that the magnitude of Z from this expression is given by Z node times square root 1 over QL square plus omega over omega node minus omega node over omega square. So at omega node, essentially we'll find this will cancel out, this one, this term with this will cancel this term at omega node, and we will end up at omega node, we'll end up with Z node divided by QL. And we said that the loaded quality QL is equal to what? The ratio between the characteristic impedance and the resistor R. And so this will equal to the resistor R. So at the center frequency, we'll find that the impedance, the amplitude of the impedance of the RLC is equal to R. Now, on the other hand, for frequencies higher than omega node, we'll find this part essentially is going to give us an increasing value with omega. So this first term will increase with frequency, while this one decreases as we increase the frequency. So essentially, this will be increasing versus frequency. And for frequencies less than resonance, we'll find the other way around. Essentially, we'll find the first term is, as we decrease the frequency, it's going to essentially decrease, while the second term essentially is going to increase. So still, we have an increasing function versus the frequencies as we decrease the frequency below resonance. Okay. And generally, from the amplitude, the magnitude of the impedance, what type of reactance that increases with frequency? We know that an inductive reactance is proportional with frequency. So here, for frequencies above resonance, the RLC circuit act as an inductive load. Essentially, it behaves as an inductor. It increases with frequency. And while for frequencies below resonance, we'll find essentially it behaves as a capacitive impedance. Okay, and capacitive because we know that a capacitive reactance is inversely proportional with frequency, so it decreases as we increase the frequency. Okay, so the RLC circuit above resonance behave as an inductive impedance, below resonance it behaves as a capacitive impedance. Now let's look at psi, the function of psi, which we found its expression as tan inverse QL multiplied by omega over omega node minus omega node over omega. So if we plot this psi versus the normalized frequency f over f node, we'll find that at resonance, the capacitive reactance is going to cancel the inductive reactance, and so essentially the phase will be zero. On the other hand, if we look at this function for frequencies and tan inverse function for frequencies above resonance, we have the phase is approaching 90 degrees. And for frequencies below resonance, the phase approaches minus 90 degrees. Or psi approaches minus 90 degrees. And again, if we have a capacitive or inductive load impedance, its phase essentially is 90 degrees. And for a capacitive one, is going to be minus 90 degrees. So again, from phase also, or psi, which is the phase of the impedance, we can conclude that for frequencies above resonance, the RLC circuit essentially behaves as an inductive load, while for frequencies below resonance, it behaves as a capacitive load.